So for this video, we're going to calculate the shear strain and the direct strain. And if you can recall, in the previous video, we have calculated our shear stress. So that was our shear stress. And what we got for that was 113.2 megapascal. And we also calculated our shear strain. And what we got for the shear strain was 198.1 megapascal. And now what we are going to do is to calculate the direct strain and the shear strain. So now the extra information that we will need to take into consideration are the Young's modulus, which we got. So that's our Young's modulus, which is our 210 gigapascal. We also have Poisson's ratio, which turns out to be 0.3, and that's typically represented with the letter V. So that's 0.3. And that's all we pretty much need in order to calculate the direct strain and the shear strain. So now to calculate our direct strain, what we need, we have everything that we need right here, either in the question or previously calculated. And if you can recall this formula that we use for modulus of elasticity or Young modulus, it's simply stress divided by strain. And if we are going to rearrange this so that we get what strain is, then that's just simply going to be stress divided by Young's modulus. And we have both of those already. So direct strain is our stress, which is 113.2 megapascal, so times 10 to the 6, and all divided by our Young's modulus, which is 210 gigapascal, so times 10 to the power of 9, and that's going to give us what our strain is, and that's just simply going to be 5.39 times 10 to the negative 4, and because strain has no unit, it's just a ratio of the change in length, then that's our complete answer for strain. So our next calculation is to understand what our shear strain would be looking like. And our shear strain, it's not going to be this time around across the length of the bolt, but it's basically going to be, you can consider it to be a shrinkage of the diameter in this particular instance. So for shear strain, now what we have this here, capital G, which represents the modulus of rigidity or the shear modulus. And similar to the modulus of elasticity, where we had stress divided by strain, for this one, it's going to be very similar, where we have our shear stress there, and that's going to be divided by our shear strain. So that's what we intend to use. And then now to find our shear strain, we just rearrange this to get our shear stress divided by our modulus of rigidity. Now there is a slight issue because we don't have a value for the modulus of rigidity. So in order to solve this one now, we're going to have to use another formula to first get the modulus of rigidity. And what that will look like is it's going to be in relation to, it's directly proportional to our Young's modulus and inversely proportional to 2 times 1 plus our V for Poisson's ratio. Now let's just put these into the equation and what we get. So that's 210 times, that's our modulus of elasticity we have there, so that's times by 10 to the power of 9, and all over 2 times 1 plus 0.3. That equals, there we go. So what we have left now is just to simply use these values in our equation that we intended to use first of all. And some of these values, they look massive because the question is simply made up, but it's just to show you the process here. So to get our shear strain now, we can just use our equation. So what we have then is our 198.1 times 10 to the 6, all divided by and then that gives us approximately 2.45 times 10 to the negative 3. And similar to the previous answer that we got for direct strain, shear strain, it's just a ratio of the change in length. So there is no unit for this one either. And that's it. That's us calculating our direct strain and our shear strain.